A block is initially at x equals 0 and in contact with an uncompressed spring. The block is pushed along a frictionless surface from position x equals 0 to x equals minus d as shown above, compressing the spring by an amount to delta x. The block is then released. At x equals 0, the block enters a rough part of the track and eventually comes to rest at x equals 3d. The coefficient of kinetic friction between the block is mu. Okay. Oops. So some things that we learned through that. This is friction. It starts at this location. We know the velocity here is 0. We know the velocity here is 0. On the axis, sketch and label the graphs of the following two quantities as a function of position of the block versus, or between x minus d and x equals 3d. You do not need to calculate the values, but you must use the same scale, and I'll explain what that means. Okay, this is versus distance, right? This is distance. We need to sketch the kinetic energy and the potential energy. So how much initial did I have? Well, I only had at this minute potential energy due to a spring, which you could have used PES, by the way, or US. And that was the only location. And I'm going to count the number of boxes, 1, 2, 3, 4, 5, 6. So I started up to here. And at the bottom, I will have, I'm going to use the same color because you're going to only have one color. So how would you have to make sure that you label them. Okay, so I would have had US or maybe PE due to a spring. That's fine, whichever one. Now here's the kicker. Wherever, I'm going to bring this down because I know that potential energy due to a spring is equal to 1/2 K x squared is proportional to x squared, so it's not linear. Wherever they cross, so I have counted 6 boxes. Wherever they cross, I better be, this is kind of a trick. This is tricky in my opinion. I actually would kind of say, okay, I'm going to come to here, maybe somewhere, wherever they cross, they had best be the total being the same. There we go. So notice where they crossed. If you added those up, it would be the same number of boxes. And that's what they mean by the same scale, because the total mechanical energy had to be the same. Okay, so I didn't have this labeled. So this is kinetic energy. I would have lost points. So I would have kinetic energy. And then I have how much energy? What happens to potential energy after it takes off? Well, it's 0 from that moment on. Well, then what happens to kinetic energy? How much energy do I have here? I have none. I have energy equals 0. So we know we end up at 0 right here. Now the question is, how does that energy, is it linear or not? Well, the change in kinetic energy is equal to work, which is work done by friction, which is equal to force of friction times d. And so it is proportional to distance. So there's no term, there's no square, there's no square root. So we are going to draw straight down. Okay, there you go. Okay, continuing on. The spring is now compressed twice as much. So now we've taken it back instead of, all right, what just happened? Instead of D, we've doubled it. Okay, so originally it was pulled back to a distance D. So we went D, now we've doubled it. Okay, so let's look and see what we've done. We originally were at D, now we're at 2D. So now the potential energy due to the spring is 1/2 K times 2D squared. Okay, a student is asked to predict whether the final position of the block will be twice as far. So instead of originally, so this is at 0, originally we went to 3D, now we're predicting, they predicted 6D. So In other words, it doubled the distance. But hopefully you see that that's not the case because I didn't double my potential energy due to a spring. I increased it by a factor of 4 because it's a squared. So the student reasons that since the spring will be compressed twice as much as before, the block will have more energy. And when it leaves the spring, will have more energy when it leaves the spring. So it will slide farther along the track before stopping at 6D. Okay, so let's highlight everything the student says. The student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring in the form of kinetic energy. So it will slide farther along the track. It will go to 6D. Now we're going to answer just answer just what they asked. Which aspects of the student's reasoning, if any, are correct and explained? How you arrived at. So BI. In fact, I would label them exactly like that. Which aspects are correct? So nothing other than what's correct. So we have highlighted in yellow what the student has said. The student reasons that since the spring will be compressed twice as much, the block will have more energy, and when it leaves the spring, it will then travel twice the distance. So we know it will have more energy. So that is correct. So the student is correct that the block will have more energy when it leaves the spring. And that is because potential energy initial of the spring is equal to 1/2 kx squared. X was doubled. Therefore, kinetic energy of the block is greater. Okay, because at x equals 0, the block will have all the kinetic energy that the spring originally had. Let's see if that gets all of it. For indicating that the final energy of the, oh, no, I want up here. For identifying that the student is correct that the block will have more energy when it leaves the spring. That's all we had to say, which we did. Which aspects of the student's reasoning, if any, are incorrect? Well, potential energy due to the spring is equal to 1/2 kx squared. Potential energy is proportional to x squared. So every time you increase the distance by 2, you're going to increase the potential energy by 4. So the distance is not doubled because potential energy of a spring is proportional to x squared. Energy is increased by 4 times. Okay. Now I'm going to go see if that would have gotten all the points. For identifying that the student is incorrect by the new final position because the spring's energy does not scale linearly with its compression. So all we had to say was that it was not proportional to x. It was proportional to x squared. C, we have to come up with an expression for a new final position of the block in terms of D. This is a factor of change problem. We know that initial energy let's actually draw the picture. We have drawn the picture up top, you can see it. We know that initial energy of the system has to equal final because it's conserved. So let's start with that. So potential energy of the spring initial has to equal, that is not true. I am wrong. We have friction. So we know that initial energy minus the work done by friction equals energy final, which equals 0, because I have no energy final because I ended up at rest. Okay. So what do I have? So again, energy initial minus work done by friction equals 0. Well, what do I have for energy initial? Potential energy of a spring initial minus the work done by friction equals 0. So we're doing a factor of change problem, just so you know. 1/2 K. Now I'm going to define my X as, so in this equation for potential energy due to a spring, we compress it by D, and then we compress it by 2D, right? So let's define X initial, the original one, as D. And we know that it traveled some distance at the original situation, the original distance 3D, okay? So if you have this little legend off to the side, it might be helpful. So X initial squared, and that X initial, remember, was what they called D, minus the work done by friction. Force of friction times the distance. I took care of cosine theta by having it as a minus, that equals 0. Now remember this factor of change of method I tried to teach earlier, and it was pretty tough at the time. Maybe you're going to see now where it comes into play. Solve for the variable that we want to know, that we're interested in. Are determining how much it changed. That solve for the variable. So what are we trying to determine? What changed? We're trying to determine how far it went, right? So we need to know D. So I want to rearrange this equation for D. So force of friction D equals negative 1/2 kx initial squared. Divide by negative force of friction, we get 1/2 kx initial squared over force of friction. Okay, so I want to know how much D changes when I change X. Well, how much does X change? So this is the factor of change for D. 1/2 stays the same, so that becomes a 1. K stays the same, so that becomes a 1. We didn't change that for both problems. X got increased by 2. Force of friction does not, the force of friction doesn't change, okay? Force of friction is constant. Force of friction is what is mu times force normal. Same exact block. All we did was change how far we compressed it. So we have 4. Factor of change is 4. So the D new is equal to 4 times the D1. Okay. So that equals 4 times the original distance, which is equal to 12 D1. So let's see if we answered the question. Express your terms. Find the new final position of the block. I just need to change my subscripts here because we have to actually show what was D1. I defined D1 as 3D, so I have to put the big D, which they had. So we have to have exactly what they had. So now there it is. It is 12D. I hope I'm not confusing you. All right, now the hard part is trying to put this in words, in my opinion. Explain how any correct aspects of the student's reasonings identified in Part B we're trying to explain this portion, what was correct, by this math that we just did. So the potential energy initial is proportional to x squared. So potential energy initial is greater Let's see if that would have got the points. For indicating that the student's correct reasoning that the block has more energy in the second situation expressed by the calculations comparing the initial energy of the spring. I don't know. This is where it gets graved for me. Okay, and then the next part is, what else did we ask? They asked, are expressed by your mathematical relationships in part C. Let's see. Explain how your relationships in part C are part C. Explain how any correct aspects of the student's reasoning identified in part B are expressed by your mathematical relationships in part C. Okay. Explain how your relationships in part C correct any incorrect aspects of the student's reasonings identified in part B. Okay. So the distance is increased by a factor of 4, not a factor of 2, because potential energy of a spring is proportional to x squared. So it's increased by a factor of 4, not a factor of 2. And for indicating that the student's incorrect reasoning that the energy scales linearly, it's not linear, it's by a factor of 4. Okay. This is the hardest part of that problem and hardest part of all the FRQs that you had. I sometimes struggle with understanding what the graders want themselves, to be honest with you. But at any rate, I hope that helps you. Like I said, these are very difficult and challenging, and over time, we will get better. All right, message me if you have any questions.